Okay.
Okay, yeah.
All right. Okay. Happy Friday, everybody. Hey, it's the weekend. I see maybe a few people missing, but that's okay. All right, let's have a recap again to get us going with chromatography. So I will potentially finish chromatography, basic chromatography next Monday. And then you'll have Gary for 2 lectures on GC, and then I'll come back for HPLC, and then he comes back for mass spec. And then that will be it for Gary. All right, so what is supercritical fluid chromatography? Anybody remembers? What is supercritical? Yes, Brittany?
Is that when you change the concentration?
Change the concentration of the grade, you mean the mobile phase?
Yeah, maybe not.
Yeah. I know, it gets, it's okay. Too much information.
If I even explain this before, but like supercritical CO2, not a fluid, not a gas, not a solid, all the things
All the things.
stopping and flowing.
You know, Michael has a good way of explaining things. But it is correct. It has to do with CO2 not being a gas. And over the critical pressure, it becomes a fluid substance, a liquid type substance. But it would be much less viscous than regular solvent. So it's more efficient, you have better resolution. And usually it's used to separate non-polar compounds that are thermally labile. That means they are not thermally stable. And so you would do this separation, and you would use HPLC type system, but the detector or columns, but the detectors used would be mostly GC. So you learn about HPLC columns later, and you know about GC detectors later, so you can put everything together. Yes.
With the supercritical CO2, similar to how in organic chemistry lab you get cold lab, like you get the CO2 from a gas or from a solid to a liquid, and then it gets so pressurized.
Solid, it's gas.
It starts from like dry ice and then it goes to gas.
Ah,
and then
I see.
and then it recondenses into a liquid due to the high pressure.
Yes, it's with the pressure. So if they use under high pressure, they compress the molecules, so the molecules become liquid state, similar to liquid state. Yeah. Okay, so what is reverse phase chromatography? Yes, Paige?
Isn't it where you have a non-polar stationary phase and a polar mobile phase?
Yes, it is when you have a non-polar stationary phase and a polar mobile phase. And the reason it's called reverse is very simple. Because they started with normal phase, they called it normal phase, which will have a polar stationary phase and a non-polar mobile phase. And then they discovered they can do the opposite. So they did the opposite and they called it reverse phase chromatography. So in reverse phase paper chromatography, what type of compounds travel the most with the mobile phase? In this case, okay, Gretchen?
The most polar.
Non-polar, you said?
Most polar.
The most polar, yes. So the most polar will move faster or move advanced more with the mobile phase, because in reverse phase paper chromatography, your stationary phase is non-polar, so your compounds that are non-polar would like to stick with the paper, and those that are polar will move along more with the mobile phase. What does TLC stand for? All right, Maya? No? You have another answer? Good.
Like, you're not.
What's that?
It's not thin layer chromatography.
It can be both. All right, how does thin layer chromatography differ from paper chromatography? Ellery? Yeah.
Either like the sorbent or the solid like item at the bottom.
Yeah, so in thin layer chromatography, you have that, what do you call it, the support. So you have a support that is not interacting with the glass, aluminum, and then you have a silica gel that you spread evenly. So what makes it different than paper is you have small and consistent particle size, which have similar thickness and have better resolution than paper chromatography. So better resolution, and resolution, that means separation, and also more consistent results, like reproducible results than paper chromatography. Okay, what's the difference between isocratic and gradient dilution?
Isocratic shouldn't change.
Isocratic, your mobile phase doesn't change over time. It remains the same concentration throughout the separation. Whereas gradient dilution, you're changing the concentration over time. What does increasing the strength of the mobile phase mean? Madison? That is one way. If you have a normal phase. So if you have a normal phase, then you start with organic solvent, and then you decrease or increase the polarity over time. So that's increasing the strength, but it differs depending on the type of separation you're doing. So increasing the strength is not always increasing polarity. It's not always decreasing polarity. It's not always increasing pH. So it really depends on what you're starting with, and you're basically giving the mobile phase power to help remove the compounds from the column or from the stationary phase. So you're helping eluting them, letting them go down faster through the column, so you have shorter analysis time. So it's basically that the mobile phase is competing now with the stationary phase. So it's becoming stronger. It can compete with the stationary phase. The molecules that are interacting with the stationary phase can now interact more with the mobile phase and move down the column. Okay. So this is kind of bringing you back to speed, but also when you study, these are good questions to ask yourself when you're studying. When you get to this point, you just say, okay, I know all of these, I'm good to go. Please.
One question from last time that I had, can you just go over partition chromatography?
Yes, actually, I will go over it as a separate section, the partition chromatography. It's coming up. Okay. Any other questions? Comments? All right, so now I'm going to go over each principle of separation or mode of separation. I'll start with absorption chromatography. I introduced all of these, but now I'm going to talk about each one of them individually, and so that the principle stays with you better. So in absorption chromatography, you have a solid stationary phase and a liquid mobile phase. So your stationary phase or adsorbent, you have very finely divided solid. That means you have very small particle size of a particular solid. It could be silica, it could be alumina, it could be charcoal. So it could be any adsorbent. And on this adsorbent, you have specific functional groups. And these functional groups interact specifically with your constituents that you want to separate. So the constituents will interact In adsorption chromatography, there are different forces. It can be van der Waals, it can be electrostatic, hydrogen, hydrophobic. So in case of electrostatic, that means you have charges. So they're interacting via charges, plus, minus, charge. So ion exchange. So that ion exchange is under adsorption. If they're interacting specifically via hydrophobic interaction, that could be hydrophobic interaction chromatography. If they are non-specific, they might be interacting in a way that separates them based on polarity. Okay. So one thing here I want to highlight is absorption coefficient is not a constant. What does that mean? So the absorption coefficient is how much of the compound is absorbed to the stationary phase versus how much of the compound is actually moving. The reason that it's different from partition chromatography, it's not constant because you have a specific number of functional groups in your compound. And it depends on the concentration of the compounds you are loading. If your concentration of the compounds exceeds the functional groups, you don't have good separation. Because some will interact and some will not have room to interact and then go with the mobile phase, and you don't have good separation. You have your compounds coming at different times. So that's why in chromatography, you want to understand how much you can load on the column. That means how much you can inject, the concentration of the compounds that you can inject so that you don't exceed the amount of functional groups. So you don't have the situation where some are interacting and some are not. You don't want that. You want to make sure that all your compounds are interacting and separating based on their interaction with the column or with the stationary phase. So if you have silica or alumina, you're basically separating based on polarity. And if you have charcoal, also based on polarity, but this is reverse phase, and these two would be normal phase. In this case, your separation is based on polarity, so that in here, the most polar will interact the most with the column, and the least polar will move faster, and with charcoal is the opposite. So what happens during chromatography, your solute and solvent are competing for active sites or functional groups in your stationary phase. So when you make the solvent stronger, then the solute will interact less with the column. And that brings us to what we talked about, the strength of your mobile phase. When you increase the strength, then your solute or component of interest that is interacting with the stationary phase will interact less with the stationary phase. Sometimes your stationary phase like silica is bonded. So silica is polar, but sometimes you bond it, you're binding it covalently with a hydrocarbon chain. C8, C18, C40. So you change the nature of silica, making less polar, non-polar, with C40, very large hydrocarbons chain, it becomes more and more non-polar for very hydrophobic compounds or very non-polar compounds. Partition chromatography. So to remind you about partition chromatography, so you have a solid support that has liquid stationary phase. So you have a liquid stationary phase, and then you have a liquid mobile phase. The partition is your solutes or compounds of interest are partitioning. That means dividing between the stationary phase and the mobile phase as they go down. As they go down, they are solubilized. They can go into the stationary phase and be soluble in it. and then get delayed. Unless you increase the strength of the mobile phase, then they would go into the mobile phase more and move down the column. So basically, they're separating, partitioning between two liquids based on their affinity to the both liquids. So you can, the elution, meaning the removal of the solutes from the column after they interact, it really depends on the nature of the mobile phase, the solvents. So you can increase the strength by increasing concentration of organic solvent or increasing concentration of water, depending on the system, or changing the pH or even salt, depending if you have ion exchange chromatography. But in this case, there's ion exchange is not a case. Forget it. Scratch what I said. I don't want to confuse you. Ion exchange is absorption chromatography. Okay, so in liquid is changing the nature of the solvents, help you with eluting the solute. Okay, so when the most polar phase is held stationary, we said that before, you have normal phase chromatography. So the least polar will elute first, will leave the column first. The opposite is true when the least polar phase is held stationary, reverse phase chromatography. Non-polar compounds will interact more, and the most polar will elute faster or leave the column faster. We're going to follow reverse phase chromatography for caffeine lab next week. So in partition chromatography, you have a coded support. So your silica can actually be hydrated silica, so silica gel. That means the water now is your liquid phase or stationary phase. Cellulose can be integrated with water, glass beads, or it can be bonded support. So stationary phase is covalently bonded to via chemical reaction to your inert support. In reverse phase, HPLC silica bonded to C8, C18, or C40 is very common. So next week, we're going to be using silica bonded to C18 for caffeine. So that would be the stationary phase that we will be using. Okay, hydrophobic interaction chromatography is a very specific adsorption chromatography. So it's adsorption, so you have solid stationary phase and liquid mobile phase. Hydrophobic interaction chromatography is commonly used to separate proteins, antibodies as well. So biomolecules that adsorb to a weak hydrophobic surface at high concentration of salt. So what does that mean? You prepare your protein solution in high salt concentration, potentially 1 molar ammonium sulfate, 2 molar ammonium sulfate. So when you have high salt concentration, the charges on the proteins are shielded. So that means you no longer have electrostatic repulsion. Then you have mostly hydrophobic interactions on the surface because now you shielded all the charges. So now your protein will interact with the hydrophobic surface. Okay, so they will interact with hydrophobic surface, and anything that is not interacting with the hydrophobic surface will be separated. So one example we use this chromatography in, if we have a mixture of proteins and carbohydrates, and I want to purify, so I have sugars, have oligosaccharides, and then I want to separate them from my protein to purify the protein. So if I dissolve my sample that has proteins and sugars together in high salt concentration and run it through the column, my proteins are going to interact, so here it is. So my proteins are going to interact with the hydrophobic surface. So the red here denotes hydrophobicity, And they're going, the most hydrophobic protein is going to interact the most with the column, and the least hydrophobic protein is going to interact the least with the column. So I can separate even proteins. And those that don't have any hydrophobicity, like sugars or oligosaccharides, they're going to go out first, so I can separate them. Now, I'm going to have the proteins interacting at high concentration of salt. So I will run a system, let's say, with 1 molar and ammonium sulfate, and then now my protein is interacting. And if I want them to separate and move down, I reduce the salt concentration. So the way I increase my strength of the mobile phase is changing from 1 molar to 0.5 molar and eventually to 0 molar. Then all of my proteins will come out. So I can build a gradient, or I can go, if I don't care about separating the individual proteins, I only care about separating proteins from carbohydrate, I can change from 1 molar to 0 molar right away and get all my proteins out. If I want to separate my protein, I can build a gradient from 2 molar to 1 molar to 0.5 to 0.25 to 0. Then I can separate even my proteins based on their hydrophobic interactions. So going back to this, so the support is hydrophilic support bonded to hydrophobic ligand. So butyl saccharose is very common hydrophobic interaction chromatography stationary phase. And the mobile phase, like I said, you start with a 1 molar ammonium sulfate. Sometimes you start with 2 molar ammonium sulfate and build the gradient down to 0 molar of salt. Then proteins will come out and you separate them from other components in the system. It's mainly used for purification. So if you've been paying attention and not bored to death, what's the answer here? Shri? Yeah. Just test how sleepy you are. Okay. With ion exchange chromatography, that's a little bit more complex, and that's where students can get a little bit confused with that, given the fact that with ion exchange, you can have so many different stationary phases. So you can have, in this example, you have positively charged molecules that you want to separate, and your resin has a functional group that is negatively charged. So the sample that is positively charged will interact with the negatively charged functional group on your resin. So then that would be called cation exchange because you're exchanging positive charges. The opposite is true when you have a positively charged functional group on resin and your sample ion are negatively charged, then you are doing anion exchange, you're exchanging negatively charged ions. So your stationary phase is cross-linked polymer. Polyelectrolytes, meaning you have a polymer with functional groups that carry charge. So you have two kinds, highly cross-linked, or lightly cross-linked. So if you have a polymer that is highly cross-linked, your pore sizes will be small. So this would be meant for molecules that are small. So you can separate amino acids, you can separate sugars, you can separate organic acids. So small molecular weights that you can have them carry charge. But for lightly cross-linked, so lightly cross-linked, that means your pore sizes are large, so you can separate large molecules like proteins and nucleic acids. So examples of polymers, the polystyrene, where you have a styrene molecule and divinyl benzene molecule. So you form a polymer here, and you have R group that are derivatized to either be positively charged, would be anion exchange, or be negatively charged, to be cation exchange. The most common, however, is a polysaccharide based. So it's polysaccharide, and then your OH groups are derivatized to carry a negatively charged group that is weak acid. Now that's where it gets complex a little bit. So you can have weak acid, you can have weak base, you can have intermediate acid, strong base, and a strong acid. So that's where the confusion happened. We already know what the difference between acid and base. Come, very simple. Acid will carry negative charge, base will carry a positive charge. And you are separating, in the case of a negative charge, you're separating positive ions, so it's cation exchange. In the case of positive charge, you're separating negative ions, so it's anions. Easy. But now you would say, why would be a weak acid and a strong acid and a weak base and strong base? What is that? So, first of all, you have separation based on ionic valence, or the load of ions on the surface of the molecule, how big the molecule is, and how concentrated that molecule is. So that all impact the separation. Now, strong acid, strong base, weak acid, weak base. Okay, so when you want to separate negatively charged, when you want to separate positively charged molecules that are very different in characteristics, they're very different in ionic valence, very different in radius. You don't need to do gradient elution. You can run isocratic elution and get them separated. So in this case, you can use, if they are positively charged, you can use acidic, strong acid. If they're negatively charged, you can use strong base. Whatever is your pH, it won't change the characteristic of the column.
Either the wording wrong or no. So it says negatively charged at any pH above 2. Would it be below 2 because it's getting even more acidic?
No.
Okay. Okay.
So when you have an acid that has, let's say, well, carboxyl, easy to explain. So when it carries a negative charge at a specific pKa and above a specific pH. When you decrease the pH, you are adding H pluses to the system. So when you decrease the pH, this is going to be like that. So it's going to lose its charge, right? It's going to gain a proton and lose its charge. If you have NH3 plus, okay, and then so it has a plus because it has an additional proton, and then you increase the pH. So let's say you're having more OH minus. So this one is going to give its proton and then become NH2. So it loses its charge. You think so?
Yeah.
You want me to repeat that?
Well, no, I understand that. It's more so just like negative charge and pH above.
So it stays negatively charged at any pH above 2. So it remains as like without a proton. If you go under pH 2, if you go down pH 1, it's going to take a proton and loses its negative charge. Strong acid has a very high dissociation factor of the proton. It really gives it and doesn't want it.
But if it's even lower than 2.
If it's lower than 2,
dissociate.
it's going to pick up the proton.
Oh, it reassociates.
It will reassociate. So in strong acid, whatever is your pH, as long as it's over 2, it's going to stay negative neutral.
Is that like the pKa influence, or is that like the?
Yeah, the pKa is very low. So pKa, it's much lower than this.
So would that be like the molarity of the solution has to be specific, or the also the?
Don't mix concentration. We're not talking about molarity. We're talking about acidity. Yeah. So when you increase the acidity and decrease the pH further than 2, you have a lot of association. Yeah, it is a confusing concept, I know. But the point here is that you have options. When you're an analyst and you know characteristics about your compound, you have options to choose from. If you want to run an isocratic and you have perfect separation, then you're good to go with either a strong acid or a strong base function. Now, oftentimes, and this is more common, your compounds are very similar in characteristics, and you're trying to separate them. In this case, you want to use weak exchangers. Weak exchangers are very much impacted by the pH and the salt concentration. So if they're impacted by pH, you can build a gradient and you can then have separation. So that you have separation and you also have shorter analysis time. So basically, if you have weak cation exchange, that means you have a weak acid. So in a weak acid situation, you can change the protonation by changing the pH. Unlike here, above 2, it's always negative. Here, you lower the pH, it might pick up protons easier than in this case. And same is the case here, you get reprotonated easier. So at potentially lower than pH 10, it can pick up a proton and lose, or give a proton, sorry, and lose its positive charge, so it will no longer interact with the anions. Okay, so you want to take a moment, not now, later, when you're studying this, to kind of have this fixated in your mind, and I can answer questions when you're ready to ask questions. I know it's a lot of information for you, so I just want you to think about it a little bit when you're studying, and maybe next week you can come back with questions to clarify. Okay. So for elution in this case, when that means after the compounds interact with the column and when you want them to come out, you change pH or you change salt concentration. With that, you can help the components interact less with the column and come out from the stationary phase in a reasonable amount of time. Okay, so what kind of interactions are dominate in ion exchange? Yes, yes, electrostatic, we're separating charged molecules. It seems I'm the only one that likes chromatography. All right, affinity chromatography. This is very, very specific and not very commonly used. It's used in specific cases when you're purifying enzymes, for example, or for purifying antibodies or purifying antigens for antibodies. So, or inhibitors, enzyme inhibitors. So it's very, very specific. And in affinity chromatography, you select functional groups that would be specific, would bind specifically with your analyte. So what happens in affinity chromatography, you have the support, and usually your support is in it. So it's not going to interact with your compound or analyte. And you have a molecule here that is the spacer. can be hydrocarbon, whatever it can be. And then you have a ligand, we call it, which is the specific functional group attached to the space. Then you have your analyte. The analyte will interact specifically with the ligand. It's like the key and the lock theory. It's very specific. So if it's an enzyme, it will interact specifically with an inhibitor. If it's an antibody, it will interact specifically with an antigen. If it is a glycoprotein, it will interact specifically with lectins. So it's a very specific type of chromatography, very specific ligand immobilized on your support, and then you're after a very specific analyte. So from a mixture of proteins, you are specifically isolating a particular enzyme. So the enzyme will be the only one interacting, for example, with an enzyme inhibitor. Okay, so when you have antibodies or enzyme inhibitor, this is a very, very specific affinity chromatography. Lectins specific to glycoproteins. So it's called general, but it's really has some specificity to glycoproteins. So the stationary phase is high surface area material, that means very small particle size, it's porous, it does not absorb anything, it's inert, and oftentimes it's agarose, cellulose, dextrin, polyacrylamide, glass, all of this material can be used as support for affinity chromatography. So elution methods, again, the first rule of chromatography is interaction with your stationary phase. The second is getting it out in a reasonable amount of time, which is elution. Okay, so you have two ways of eluting your compounds, either by changing the pH, ionic strength, or temperature. Because when you have an enzyme and an enzyme inhibitor, for example, you need specific conditions for them to interact so that they have the right charges, they have the right hydrogen bonding happening, hydrophobic interaction happening. So by changing the pH, you change how the characteristics are on the surface of the molecule. When you change pH or ionic strength or even temperature, there's optimum temperature for interaction. So when you change those characteristics, you loosen the interaction, you weaken the interaction, so analytes will come up. This is called non-specific elution. Biospecific elution is usually used when you have lectins that has a general ligand here. So what you do is in your mobile phase, you add the same compound that is attached to your stationary phase, you add it to the mobile phase, then your compound now will interact with the ligand freely flowing in your mobile phase. We call that biospecific elution. Excess ligand in the element or your mobile phase. These are all terms mean the same thing. Eluent, mobile phase, or whatever you use to elute your analyte. All right. Yes. Yes. No, you don't want to get into interaction. And then this is first going to change your analyte, and it's very hard to create losing. So, which of these interactions happen? Show a faded sequence in this. Michael,
Hydrogen bonding.
what else? Okay, Elisa. What else? Huh? Electrostatic. What else?
It's a trick question, no.
All of them. All of them can happen.
It's a trick.
Trick question, you didn't have like
I know,
more than one there.
I know I did it now. I was speaking there.
Are we looking for the tax one or the structure?
Structural arrangement is very important because structural arrangement dictates what functions are on the surface. If you have OH, then you can have hydrogen bonding happening on the surface. If you have hydrophobic functional groups, it will cause hydrophobic interaction. So the structure implies what's on the surface, implies what kind of interaction can happen. All right, size exclusion chromatography. So this is physical separation. So what you have here is you have your packing material that shouldn't be interacting with your compounds. So you have your packing material made up of particles, and you want them to be as small as possible, but then the particles have different pores. So they're porous, okay? Each particle has different pores. And usually when you are running size exclusion, you can choose a range of pores size. Because depending on the size of the molecules we separate, you would have range of pore sizes to select from, so you have a good separation of your compounds of different molecular weights. So, and then you inject your sample and you have different sizes of your molecules. One is so large, and one is medium, and one is very small. So what happens in this case is the large one is going to go through what we call void volume. It's too large, it can go in any of the pores. It doesn't fit. So the largest elute first in the void volume. Oftentimes, to determine the void volume, you run a very, very large molecule like blue dextrin. You run it through and you can determine the volume it took for this large molecule to come out. You can determine your void volume. The medium is going to go in and be able to go through this and go through this hole or pore, and will be delayed because now it went into the particle. It will be delayed, but it cannot go into this small one here, the small. This one is going to go in here, there, everywhere. It has access to all the pores, so it'll be delayed the most. And it will elute last. Because it's very small, it has access to all the pore sizes. So in size exclusion chromatography, the largest molecule will come out first, the smallest will come out last. So this is basically illustrates the drawing where you have large versus small. The large is larger than all of the pores, so it doesn't go into any pores. It leads first, and the smallest have access to all of the small ones, and you get separation. Okay, so parameters that you would need to know in size exclusion, because if oftentimes we use size exclusion for purification, but also for identification of molecular weight. So it can be used to determine a molecular weight of your compound, and that you usually run standards. So you would run standards that fit the entire volume, or what we call it total permeation volume, which is the void volume plus the internal volume. The internal volume is the volume of all the pores in the particles that are in your compound. So the total volume is void volume plus internal pore volume. And then you have your void volume, the volume of everything outside the particles. And then you have the volume of elution. So elution volume is the volume required to elute a certain solute. That means an X compound. You want to choose a range where your X compound can elute within that range. So you would have like 10 milliliter until your compound of interest elute. Let's say this is 5 milliliter, let's say this is 20 milliliter. Then you have your volume of elution. Why are these all important? Because you use them to calculate partition coefficient in this case, which is for every compound, for any specific compound, volume of elution minus void volume over total volume minus void volume. So you get a coefficient that you can plot on your y-axis, and on your x-axis you have the log of molecular weight of standards. Then you can get a prediction equation for the molecular weight of your actual unknown sample. So you would have K value for every molecular weight of a standard solution. You have standards, and then you plot this, and then you have an unknown, let's say, that has a 0.8 K value. You can determine its molecular weight.
What's VT?
What's that?
What is the VT stand for?
VT total.
Oh,
So VT is the void volume plus the internal particles pore volume. This one. Okay, so VT equals the void volume plus the internal pore volume is the total.
I had a question on this. This is volume, it's not volume of the mobile phase, but volume of the sample.
No, volume of the mobile phase. So it's like usually we call retention time. So you can either have a retention time or you can calculate the volume that took for the sample to come out. And usually you calculate that with time and with the flow rate.
From mobile phase.
Yeah, mobile phase is usually water or buffer. Yeah, of course. Well, if you want your sample to move with something, so you have your mobile phase, water or buffer, and your molecules are just separated physically by size. Okay, so now the last question of the day. None of them. There is no interactions. It's physical based on molecular weight only or size. Okay, this is a very important study table. We will start with it next time, but it kind of summarizes everything we talked about. The separation mode or mode of separation. And then for every mode of separation, what would be the stationary phase? What would be the mobile phase? How you would, this is blocking. How would you increase the mobile phase strength? In each case, how you would increase the strength of the mobile phase? What would you use first and what type of interactions take place in all of these? Okay, so this is a good study table, and then please do review this over the weekend. Come back on Monday with questions for me, and happy weekend.
Thank you.